Hi everybody, I'm the greatest living inventor, and today we are doing my invention, passive anti-freezing regulator. So I'll write it down. Passive anti-freezing regulator. Okay, so problem. This idea came after watching a few documentaries where people couldn't breathe because the regulator failed. Okay, a regulator is part of the oxygen. You have an air tank with a high pressure, like 3000 psi, and you need a lot of atmosphere, and you are a diver or a mountaineer, and you breathe with an air tank, but you need the air to be in a low pressure, like if you are 10 meters down underwater, then you need 2 atmospheres. Okay, so if you are in here, then in ground level, then you need 1 atmosphere. So it's the regulator has 2 steps, 2 stages. Once the first stage, bring it from 3000 psi to a pressure of 140 psi, and the second stage, which is near your mouth, brings it to the pressure that you actually need, even lower pressure. Okay, so in our Everest challenge, these are documentaries that you see the problem. Our Everest challenge. I'm giving you the link to docuwiki.net. Okay, this is the website of MV Group that I always download the documentaries from. So you can see this you can see this documentary, Our Everest Challenge. I'm giving you the link in the description. Near the peak, Ben, the climber, had to change one regulator and then another one. And luckily he had them from the Sherpas, or otherwise he would not be able to breathe. In the series How the Earth Works, in the episode Will Iceland Poison the Skies? So I'm giving you 2 links. I didn't find a link like this one. It's not on DocuWiki, I'm telling you what I've seen on TV, and there is even a link I'm giving you to Twitter on when Liz Bonin visited this place, Iceland. Immediately when entering the water in Iceland, Liz's regulator failed. Okay, I'm just taking my shirt off. Okay, so and I've seen it in Cooper's Treasure too. Okay, so it's not like a good show. I've just seen it when I do dishes. I watch Discovery and National Geographic and Discovery Science, and I saw this by accident. But anyway, in all these shows, and I guess more, it happens in real life all the time. You see this failure in the regulator. Okay, so now you know that there is a problem. Okay, the reason for this failure is that when gas goes from being squeezed in a tight place to a place where it can expand, the gas cools. Okay, it becomes cold. Wikipedia, Joule Thomson effect. Okay, so this is all because of Joule Thomson effect. Okay, which you can see in Wikipedia. You have a gas in a small place. It goes through a nozzle to where it can expand, like in the refrigerator or the air conditioning. It's the same thing. This is how we cool gas. We take it from being compressed to being expanded. So this is how the regulator freeze and fail. If this cooling is too much, the regulator valve freezes in its open state and all the air runs away, which causes even more freezing. Okay, so I'm giving you soon links so they explain it better. But anyway, there is I'm erasing and trying to explain really quick. Okay, so if I'm trying to show you how a regulator works, regulator, there is the air tank. Okay, and this has like a tap, like something that you rotate, and this is connected. Again, I'm just doing the schematics. I don't know how it actually looks like. I've seen it on the YouTube videos that I refer you to. And from this, you have, this is like 3000 psi pressure, high pressure. And from here you have another stage. Okay, this is a, I don't know how to draw this, so I'm just drawing a box. This is the first stage. And this gives us 140. I'm just closing the door so there is less noise from the outside. So this is like 140 psi. And from here you have the regulator, which looks like it has a place where the air comes in and the place where when the air comes out. When you inhale, you take air from here, from the tank, and when you exhale, it goes out to the water or to the environment if you are in the mountain. So so let's do this also schematically. So there is if you want to see the real thing, look at the videos that I'm giving you the links to. So you have here a valve. Okay, this is like a valve, and it has it has a spring. Okay, and the spring is pushing the valve, so it closes the valve, okay, all the time, except when you breathe, and then there is like a diaphragm, which is like a rubber sheet, okay, rubber sheet. Sorry, sheet with an E, sorry. It's not my mother tongue, and it's like 9:30 in the evening. So, and I have attention deficit disorder. Okay, so this diaphragm, let's do this in pink. Okay. So it's here, and when it's connected to the there is a lever. Okay, this is the diaphragm. In pink, and this is a lever. I'm not sure how it's connected, but it's connected, and it's like connected to the diaphragm. When the diaphragm moves, it moves the it gives the air entrance to get inside to the regulator. Okay, so let's say this is a lever. Okay, if you want to see it more realistically, look in the YouTube video. But what this does, that when you inhale, this opens the valve, and the air can come into the regulator, and you can breathe it. Okay, and when you blow, like exhale, then there is another valve, something like this. Okay, another valve that doesn't let the water to get in, but it lets the air come out like bubbles if you're in underwater. If you're just in a mountain, then out, the CO2 gets out and you don't see it, but it's out of your regulator. Okay, so the regulator, it's next to your mouth, and you can inhale, get fresh air with oxygen, and exhale, and then it's this closes and this opens and the CO2 gets out. The used air gets out. Okay. So you have more schematic idea, but you can see it. We can see how the regulator is built from the inside in this very nice video by Jonathan Bird. Sorry. Jonathan Bird. Okay, so this video is called How Do Scuba Regulators Work? Scuba 101 by Blue World Plus. Okay, so how do, I'll write it here. Jonathan Bird, how do scuba regulators work. And this is from Scuba 101. By Blue World Plus. Can you see the plus? Yeah. Okay, so this is by Jonathan Bird. I think he makes this channel, this YouTube channel, and it's really nice. You should see it. He actually takes apart one regulator and shows you exactly, he demonstrates. It's really, really nice. Okay, so how do scuba regulators work? I'm giving you the link in the description. Okay, so we are 19 minutes into the video. Just drink a little. Okay. Sorry. Also, we can read about the freezing problem. Okay, this is the normal way of the regulator to work in the video, but you can read about the problem in Wikipedia in a mechanism of diving regulators, hashtag regulator freezing. Okay, so in Wikipedia, mechanism of diving regulators hashtag regulator freezing. Okay, so this is the problem. This is like the normal functioning. This is the problematic, the problem that we are trying to solve. Okay, so there are mechanisms that take a little warmth, heat from the environment, but underwater and in high mountains the environment is very cold. Okay, so these are solutions that don't work, that are not good, and also there are solutions that are active, like they need a battery or something, and my solution is passive, it doesn't need a battery. Okay, so, and it's important because under pressure and stuff, a battery might not work, or okay. So now I'm erasing and I'm starting to explain the solution. So far it was the problem, especially this is the problem, regulator freezing. Okay, so now I'm erasing and explaining the solution. Okay, so a solution. We cannot use the warmth of the exhaled air that comes out from our mouth, because one, this air needs to get out as freely as possible to get rid of the CO2. Sorry. Sorry. I tried to sneeze and okay, so second, two, this air has, so I'm reading again, we cannot use the warmth of the exhaled air that comes out from our mouth, because one, this air needs to get out as freely as possible to get rid of the CO2. Two, this air has moisture which we must get rid of. It might even freeze and create dangerous ice crystals that we might breathe. Okay, and it makes laryngospasm and all kinds of problems. And three, the air we breathe out is at a constant temperature, and here we prefer something responsive, which can be not warm at all or very warm, depending on the situation. Okay, if the regulator froze very badly, we need something very warm. If it's just starting to freeze, then we don't need something so warm. So, and our breathing is all the time in the same temperature, like 37 degrees Celsius, like our body. Okay, so what we need is something simple that works without external energy and without moving parts. But we do have a part here that is moving fast, the air through the valve. Okay, this air that is coming fast. Remember, we have this this is in and this is out, and here if it's going fast, then this gets stuck. Remember, there is this spring, but if the spring is freezing, okay, if I'm showing you in cyan, in light blue, the air, let's say the air is coming in this tube and is coming through here, and here it expands. Remember, so it expands, so it takes out more room, so it gets cold. This air is now cold. Okay, so it makes this spring cold. So let's make it in blue color, because now it's cold. So this is now, okay, this spring frozen. Spring. So the spring is frozen because it's the air is cold because it expands. And now, because it doesn't work, it doesn't close this valve. This valve is frozen too. Okay, this is a frozen valve. So this creates a feedback loop that now even more air is coming faster. Okay, and it's like faster air, it gets colder, it gets more frozen, and more air is coming. You see it's a vicious circle. Okay, it's like a feedback loop, but positive, but to the bad side. Okay. And this is when this stays open and all the air gets out. Okay, because we cannot breathe all the air, so all the air gets out until the air tank is empty. Okay, so this is how you lose all the air in the tank, when the regulator fails. Okay, so this is what you were supposed to read in Wikipedia. Okay, so now the solution. So solution, we cannot use the warmth of the exhaled air. We talked about it. So we need something simple that works with external energy and without moving parts. But we do have a part that's moving very fast, the air. That's the air through the valve. Okay? This light blue, this cyan, the air. So the air is moving very fast when this problem happens. So with preparation in advance, we can use this as our source of energy. First, we need the air in the tank to be ionized. Okay, what does it mean, ionized? Like, if there is, I'm not explaining now like in length, But basically, if you have some molecule, like you have an atom, and it has an electron, which is minus, and a proton, which is plus. Okay, this is proton. Okay, so this is basically an atom. There are neutrons, but basically this is how an atom looks. And if you take away the electron, then it's ionized. Okay, now instead of the whole thing being plus and minus being neutral, then if you take away the electron, then this atom now is positive, because there is nothing to balance this proton. So far there was an electron, but we took it away. Okay, so this is what it means to be ionized. So in this example, this was an atom of hydrogen, but you can also make ionized air, like ionized oxygen. Okay, so air is made of nitrogen and of oxygen. So instead of being just neutral, you can make the oxygen with a plus or a minus, and then it's ionized. Okay, so we want ionized air. Okay. First, we need the air in the tank to be ionized. So remember, we have the tank. Remember, there is this first stage and the second stage and so on. This is the second stage. And this air tank becomes ionized air tank. Okay, this is now ionized. Ionized air tank, which means it's like the atoms of the oxygen and the other gases like nitrogen, but not in their original version, in electrically charged version. It has either plus or minus. Okay, so what we need is, first, we need the air in the tank to be ionized. We need to make sure there is no ozone. Okay, so if we have oxygen is what we breathe. It's like two atoms connected together. And if you have ozone, it's not good. It's poison for us. And it's like it has, I'm not sure how many lines. Sorry, I don't know much chemistry. But this is, oxygen has its O2. So it has two oxygen atoms. And the ozone has three. Okay, ozone is O3. So, but we don't want the ozone. Ozone is bad for us. Okay, So no ozone. We just want oxygen, normal oxygen, but without some of the electrons. Okay? Or anyway ionized, either with more electrons or less electrons. Okay, I don't know enough chemistry for this, but it's possible to ionize oxygen. There is even there are machines to do this. Okay, so we need to make sure there is no ozone. Okay, ozone is bad, it's poisonous. Wikipedia, air ionizer, ions versus ozone. Okay, so Wikipedia, air ionizer, hashtag ions versus ozone. Okay, so after ionizing the air, we cycle it through a filter with freon. Okay, freon is also poisonous. Freon. Okay, so I'm just drawing you a skull so you know that this is bad. Okay, this is supposed to be a skull, it's poison. And also this is poison too, the ozone. I don't have room to paint the okay, so this is ozone is bad and freon is bad. But the freon helps us to get rid of the ozone. I'll explain. Okay, they are bad, but this helps us to get rid of this. And after that, we get rid of this also. So after ionizing the air, we cycle it through a filter with freon. That's the thing that made the ozone hole. Okay, so this decomposes the ozone into oxygen. Okay, so that was the ozone hole, which I'm sure you know of. And if you want to see in Wikipedia, it's called chlorofluorocarbon. Chlorofluorocarbon. Okay, it's one word, it's just a long word. This is the type of freon that is made the ozone hole, that damages the ozone, which catalyze the breakdown of ozone, O3, into oxygen, O2. Okay, so here we have O2, but charged. Okay, let's say minus, okay, or plus. I'm not sure, but it's charged. I'm putting an asterisk so you know it's charged. Ionized. Okay. It's the same thing. Okay. So, okay, so we don't have O3, we have O2. How come? We killed the O3 with the freon, which I don't know I think it's a CFC, the CFC, okay, the acronym. Okay, and now we have only O2, and this O2 we put inside the tank and pressurize. Okay, so we need to do this in advance, and it's O2 with a plus or minus. Okay. It's charged, ionized. Okay, so you can see in Wikipedia, ozone depletion. I don't have room. Ozone depletion. So this is how the freon took away the ozone. Not all the ozone, or we would be dead. We need the ozone in the upper atmosphere, but some of the ozone was damaged, and it was because of these gases that were used in refrigerators mainly, and then we switched to other gases that don't damage the ozone. Okay, so so you can see this in Wikipedia. Okay, so and this freon is closed inside a cell with membrane walls. It only operates on the cycled air while that air passes in the freon's closed cell. Okay, so we basically have a system. I'm telling you how to make this O2 without ozone. We have like a system that is in a closed loop, and inside the system there is also a cell. There is a pump. Okay, let's make it like this. This is the pump, and there is also pump, and there is also a cell with the freon. Okay, so this cell has membranes, like filters, where the air comes in and comes out, which are too big for the CFC to this. Here it's the CFC. Okay, this is CFC. It's just the C, chlorofluorocarbon. Okay, so this is CFC. So here there is CFC. When this air with O2 and O3 is going in, let's say it's this way. Let's do it this way, so it's with the clockwise. So the air is coming here, and is the O3 decomposes into O2. Okay, so and then it goes again, and all the O3 is cleaned. There is no ozone. Okay, and we take after this, and the CFC is closed here. It's a big molecule that is also only the catalyst for the process of turning O3 into O2. And after this, we take, like from here, the clean O2 and pressurize it into tanks of ionized air tank. Okay, so what's the time? 45 minutes, so I need to hurry. Okay, so this freon again, because it's poisonous, is closed inside the cell with membranes walls. It only operates on the cycled air while that air passes in the freon closed cell. After it comes out, there is only clean O2 without CFC and without O3. And we can make another pass through this, but when we take it out, the air is clean. This is clean air. It's with nitrogen, but nitrogen is not poisonous. It's just normal air. Okay, it's more complicated. It depends on how deep you go. It can be poisonous when you dive. But I mean it's not with ozone and it's not with CFC. Okay, so so in the end of the process, we just take air without the freon, and now it's without ozone. We compress the air and put it into tanks normally. It is safe to breathe, but it now also can be used as our electromotive force for our heating system. Okay, so now this thing this ionized air is our electromotive force. Which means it's our source of power in the like our battery. Okay, this is what gives the electricity that we will need. Okay, for example, if you have an electric circuit, if you have an electric circuit, that has some lamp. Okay, this is a battery, and this is a lamp that gives light. Okay, and the battery gives power. So I hope I'm drawing this correctly. Forgive me if I'm not. But basically, the battery is called EMP. EMP, meaning electromotive force. Okay, this is the initials. Okay, this is what pushes the electrons through the lamp, through the part that gets hot, the filament, and gives light and heat. Okay, so we don't want light, but we want heat, and we'll talk about it. Okay, so it's not that simple. We don't just want a resistor, but we want something more advanced. I'll talk about it. Okay, so in the case of freezing open of the valve, remember it's stuck, it's frozen. So in the case of freezing open of the valve, the air starts to flow fast, which means fast flow of charged particles, because our air is now ionized. So it's a fast flow of charged particles, electric particles. Okay, so from here the process is very similar to induction cooking. Okay, so I'm going to write it here. So this is just the same as induction. cooking. And for me it would be more like hand waving, because I don't know exactly how to do the coil, but induction cooking is something that happens in a lot of kitchens. Okay, I don't have it at home, but many people do, and it's like it can heat something without touching it, because it inducts this field inside the metal, and this is made of metal, and this is made of metal. So if this contains iron, then we are good. We can do induction cooking. Instead of heating a pan or a pot, we heat a valve or a spring. Okay, so that's the main idea. And what's moving is not just electrons in a wire, it's air molecules in a tube that looks like a coil. So this tube okay, this is the rubber tube. So we need to make it like a coil. I don't know how to draw it in here, again, because I don't have the background in electricity, but it would basically it will go around this mechanism, and only then like get inside the chamber. So maybe it will go to here, and from here make this round, and then be released here. Okay, so we need to make the same thing that we have with the induction cooking, which we have a spiral in our where we cook. So we need to make something similar inside the regulator. Okay, this is the regulator. Okay, so from this part I don't know enough about electricity, so someone else needs to come with the exact details, but all the parts are correct. The electricity needs to flow in a coil, so we make the flexible air tube wrap around like a coil, close around the valve, before connecting to and feeding the valve itself. So now, when the valve is stuck open, frozen, there is a magnetic field inside the coil. The valve needs to be made of something that contains iron. Like the pen needs to be made of something that contains iron when you do induction cooking. Like if the pen, what you cook inside, is not from iron, like it's from aluminum or from copper, then it's not good. It needs to contain some something that a magnet can attract. Okay. So now when the valve is stuck open, frozen, there is a magnetic field because the air is moving rapidly through this brown tube, and then it makes it makes a current. Okay, it's particles that move fast, and the particles are charged. So they create a current and they create a field. So there is a magnetic field inside the coil. The valve needs to be made of something that contains iron. You can check it like they explain here. If a magnet sticks to it, it contains iron. Now this is a video how induction cooking works by GE Appliances. Okay, so I'm giving you the link in the description. So now there are, I guess, turbulent magnetic fields inside the iron. the valve warms and unfreezes, thaws. Okay, so this is unfreezing. It gets hot. And this gets hot too. Okay, this is the spring, and now it's not frozen. Okay, this is a thaw. Or unfrozen. And this is also unfrozen. And now, because it's unfrozen, then this closes. Okay, it's like it's not stuck anymore. So this stops being induction cooking. It stops being hot, and now it's normal. So it becomes black again, normal. Okay, so we balanced. It's like instead of a negative, it's like instead of a positive feedback, it's negative feedback. It brought it to the normal situation and stopped. This is what we started with. This is the normal situation. Okay, so now there are, I guess, turbulent magnetic fields inside the iron. The valve warms and unfreeze, thaw. So now the valve is unstuck and closes the flow of air. Okay, so now it's unstuck. And this is also unstuck. Okay. So now there is no charged ions flow. Okay, we closed this fast air, and now there is no charged ion flow, so no magnetic field, so no heating. We return to normal automatically. What is induction heating? How does it work? See live demonstrations by EFD Induction. Okay, this is another YouTube video. It's nice. It shows how focused this induction cooking is. It can heat just the part that you want. So it doesn't hit your mouth, or it doesn't hit your the whole mask, just the part that is inside the coil. So you can really control what you want to heat. It's not like normal heating. It's very focused. And it's also without touching. If I didn't explain, it's without touching. You don't have, the pen doesn't need to touch the coil. Okay, so I'm giving you the other link too. It's called What is Induction Heating? How does it work? See live demonstrations. It's by EFD Induction. I'll give you the link in the description. Okay, and 59 minutes. I need to really hurry. In this video, we also see that it's very focused. So the rest of the mask will not hit, which is good. Because our electrical current is direct current, DC, and the okay, this what flows here is the direct current, DC. And induction heating works on alternate current, AC. So this needs AC, and this is DC. Okay, so we have a problem. It's not the same. So we need something to change the electricity from DC to AC. This is called a power inverter. Okay, so we need a power inverter. Which you can see in Wikipedia, power inverter. Static inverters, solid state, do not use moving parts in the conversion process from DC to AC. Okay, so just a final remark. I hope one day such regulators will help people explore personally, not with robots, personally, the mountains of planet Mars and the oceans of the Jupiter's moon Europa. Okay, so that was my invention. So I hope it was clear, and I'll see you in my next invention. So thank you very much. Bye bye. Thank you.